Okay, welcome everyone to a session on analysis of complex systems. We have 4 talks in this session, and I'm delighted to welcome the first one. Weijiang is the speaker, and he's going to talk to us about trace abstraction-based verification for uninterpreted programs. Go ahead.
Oh, sorry. So can you hear me? Is there something wrong here? Okay. So
yes,
this
you can
is
hear me.
This is a joint work with Professor Zheng Bangchen, Yi Du, and Professor Qi Wang. Let's get started. First, let me introduce some backgrounds of uninterpreted programs. An interpreted program is a kind of program which involved uninterpreted functions, especially an uninterpreted function f only has a function signature, but no other definitions. For example, the left one shows an example of uninterpreted programs. Initially, the variable y is assigned to x. Then, if x is not equal to z, the program will execute the loop body and update x by applying uninterpreted function f and g in order, while update y by applying g and f in sequence. The loop body's execution is repeated until x is equal to z. Finally, the program checks the assertion, that is, x is equal to y. The third statement requires the condition holds for all possible traces at this point. Especially as an uninterpreted program, the verification question here is to check if the assertion holds for all possible interpretations. Apparently, if both f and g are interpreted as identity function, the assertion holds. While the assertion doesn't hold if f is interpreted as an inverse value function, while g is the absolute value function. Therefore, the answer for this verification problem is definitely not. For such verification problem, we usually transform it into the right one by replacing the assertion with an assume statement and the conditions negation. Then decide if all traces of this new program are invisible, which is a reachability problem. Notice that these 2 problems are equivalent. That is, the assertion of the left one holds if and only if there are no feasible traces in the right one. But unfortunately, both the problems are undecidable. For such undecidable verification problem, there are several work dedicated to finding the decidable subclass of uninterpreted programs. They find that for loss, uninterpreted program satisfies coherence, which consists of 2 properties, memoizing and early assumes. The coherent UP's verification problem is decidable. However, here we want still explore the problem that how to verify the general other than coherent uninterpreted programs efficiently. And this is also the problem this work solved. Next, we introduce our trace abstraction-based verification method. Our verification is in CEGAR-Style. The verification target now is given a program P, checking whether all traces of P are invisible. For such problem, the CEGAR-Style verification is like, first, we randomly extract a trace from P and check its visibility. If it is invisible, then we can deduce a set of invisible traces. Next time, we extract the trace outside of this area to check its visibility. If it is invisible again, do generalization and repeating such process until all program traces are covered. Then we can conclude the program is correct. Or during the process, we might find a visible trace, which is the counterexample violates the assertion. Then the program is incorrect. Note that this process might not terminate. Now, consider such styles verification for general uninterpreted programs. Our observation is that if the program can be split into different parts, the coherent ones and the non-coherent ones, then our first key idea is we can utilize the the existing decidable verification method to solve this part. And the decidable verification has a piece-space complexity. And the second key idea of our work is that we can design a specific trace abstraction method for UP's traces to improve the verification's efficiency. Next, we use a motivation example to illustrate our method. We need to check if all traces of this program are infeasible. First of all, such program is not coherent due to the else branches execution violates early assumes. Then to verify such program, we can first split such program into several subprograms based on the control flow graph. Like that, the first subprogram corresponded to the if branch, which satisfies coherence, and the second subprogram corresponded to the else branch, which do not satisfy coherence. For coherent part, we can verify it by the decidable verification, which is the existing work. Then for non-coherent part, we propose a congruence-based trace refinement to do the verification. Next, we mainly focus on this part. Consider the program. We want to check if all traces of this program are infeasible. We check it in CEGAR-Style and extract a trace which executes the loop body 3 times. For better illustration, such trace can be represented as an automata like that. Each state represents the program's information collected before executing the statement transition. Next, we check the trace's feasibility. If it is feasible, then assume statement is satisfied, which implies the assertion violates. Further, P is incorrect. While infeasible implies nothing until all traces are checked to be infeasible. Then we can conclude P is correct. Notice that for coherent traces, we can use the state transition to check its feasibility. Since the usage of uninterpreted functions, we mainly focus on the equality relation of variables. Therefore, during transitions, each state is denoted as a tuple, shown in the left, which consists of the equality relation, the disequality relation, and the function relation of program variables. For example, assume that we arrived at a state whose tuple implies x and y are equal, and there is no disequality and the function relation between variables. Then if we execute the statement f of x is assigned to x, the next step is like the equality relation between x and y is removed. Instead, we add the function relation between x and y. Then we back to the last state, and if we execute the statement, assume x is not equal to y, then we can find in the next state wherein both x is equal to y and x is not equal to y hot. There is a conflict, then the trace is infeasible. As we can see, such state transition solves the feasibility checking problem nicely. However, unfortunately, such method can be applied to coherent traces only. While this trace is non-coherent, but fortunately is such non-coherent trace can be easily translated into the coherent one by adding some additional variables to make it coherent. Note that such additional variables would not change any analysis results of this trace, since they are never be used except make it coherent. The reason behind we will not describe here, and this is the work done by one master. Then we can check its feasibility from the initial state. Then after several transitions, we got the final state. A conflict between the equality and the disequality relation reveals this trace is infeasible. Next, based on less calculated states, we notice that exclude lot states R0 to R3 brought by additional variables. For the second iteration and the third iteration, we have the state Q8 and Q12, Q9 and Q13, Q10 and Q14, Q11 and Q15 are equal to each other. Then we can deduce that there is a repeated transition sequence. Then we can remove lost states and add a new transition from Q11 to Q8 to abstract such invisible trace. Now we know that all traces that execute the loop body twice or even more times are invisible. In CEGAR-style verification, after such abstraction, we can get rid of these traces to check other remaining traces, which is represented as an automata subtraction. Now, we only need to verify the two traces left, which is easier than to verify all possible traces in the original automata. And we can finally prove that the program is correct. Now, let's reorganize the whole process and introduce our verification framework. Initially, the general uninterpreted program is split into coherent parts and non-coherent parts. For each one in coherent part, we use the decidable verification to solve it. While for each one in non-coherent form, the congruence-based trace refinement method to solve it. As for the verification result, only all sub-programs are verified to be correct. The original program is correct. Okay, the final part presents our experimental evaluation. Note that, as far as we know, there is no existing benchmark can be commonly used for such verification problem. And we conduct the experiment on two benchmarks. The first benchmark consists of 50 automatically generated programs, wherein each contains both coherent and non-coherent sub-programs. While the second benchmark consists of 46 programs extracted from SV competition's loop category, wherein one is either coherent or non-coherent. For baseline, we compared our method with the state-of-the-art Ultimate Optimizer, which is implemented based on the interpolation-based CEGAR verification method. And the verification time is set as 10 minutes. And our prototype is also provided on this repo. Here is the results of effectiveness and efficiency between Ultimate and ours. We focus on the number of programs successfully verified and the average verification time cost on both benchmarks. For the first benchmark, we successfully verify all programs with a 3.6 speedups, while for the second benchmark, we successfully verify a program with 1.9 speedups. The results show our method is effective and efficient. We also consider the influence of partition module and the congruence-based abstraction module. Therefore, for 25 correct programs in benchmark 1, we compare the verification performance under different configurations. For example, the partition with congruence-based abstraction and the partition with interpolation-based abstraction, and of course, Ultimate, wherein our method, that is the red one, performs better on 17 programs, while the other two performs better on 2 and 6 programs respectively. Therefore, we can conclude both partition module and the congruence-based abstraction module are important for the verification performance. Finally, let's conclude. For general uninterpreted programs whose verification problem is undecidable, based on some observations, we propose the first key idea that the program can be split into different parts, and one of them can be solved by the decidable verification. And the second key idea that we can design a specific trace abstraction method to improve the verification's efficiency. Such verification framework has been implemented as a prototype, and the evaluation result is promising. For more details, you can find it in our paper. That's all. Thanks.
Thank you very much, Weijiang. Do we have any questions? Okay. So feel free to add questions in the chat or to raise your hand and speak if you have a question. Maybe when we're waiting, give people a chance to think. Could you tell me a little bit more about how you partition the programs? And so you showed the example on slide 6 where you partitioned it based on the if statement. But can you talk to me in general about how you do that?
Yeah, actually, currently we partition the program based on the control flow graph, and currently we treat the we only treat the while loop statement as atomic and only divide those if else branch statement. And of course, the number of the subprograms is exponential with the number of if then else branch statements. But actually, there is a trade-off between the benefit and the overhead brought by the partition. So maybe in the future, we will design some heuristic method to partition the module, the partition program. Yeah.
Okay, interesting. Yeah, I was just curious in terms of, you know, if you partition it differently, how much of an impact it has and what that trade-off is. So, yeah, interesting. Okay, and in terms of future work, I know you said in your paper that you hope to extend it to systems where you had dynamic memory. Can you comment a little bit on that?
Yeah, actually, it's one of our future direction. Actually, we want to apply this to you know, currently we are focused on the verification of the uninterpreted programs, right? And currently we want to apply these results to the real programs verification. You know, the uninterpreted program is actually the over approximation of the program. So we want to use it to make some pre-analysis, maybe before you do the verification.
Yeah. Okay.
Yeah.
Okay. Thank you. Anyone else got any questions? No? All's quiet? Okay, well then I'll just say another thank you to Weijiang. Thank you very much. And we'll move on to the next speaker.
Okay.